All right. Welcome, everyone. We've got a really fun seminar set up today with the Nature Review Physics, looking at machine learning and fluid mechanics and their interaction. Before we get started, I wanted to let people know this is going to be recorded, and these videos will be available online in a few weeks. I also wanted to let you know that we're going to have 2 talks, and then we'll have a period of time for question and answer. And there'll be a Slido link up in the chat for everyone, and you can put your questions up there and we'll curate through them and pick a few to discuss after the 2 talks. When you do ask those questions, please do indicate which speaker the question's for. I also wanted to remind you that this is a series of talks, and there's another talk next week at the same time on high energy physics. All right. So again, thank you for joining. My name is Gabriel Weymouth. I'm a professor of hydrodynamics, and I'm very pleased to be chairing this session on machine learning and fluid mechanics. And today we have 2 really great speakers, Laura Zana and Steve Brunton. Professor Laura Zana is a professor of mathematics and ocean and atmospheric science at the Courant Institute at New York University. She was faculty at Oxford until 2019 and obtained her PhD in climate dynamics from Harvard. Professor Zana's group aims to advance the fundamental understanding of ocean dynamics. And the goal of that is to improve climate change predictions, among other things. Her group's been focused recently on the development of physics-aware machine learning models to deepen the understanding of climate processes and to bake in some amount of physics to these otherwise kind of free-flowing machine learning approaches. She is the recipient of the 2020 Nichols Award for American Meteorological Society for exceptional creativity in the development and application of new concepts in ocean and climate dynamics. So that's pretty exciting, and we're really looking forward to what she has to say. Our other speaker is Dr. Steve Brunton. He's associate professor of mechanical engineering at the University of Washington and also adjunct professor in the E-Science Institute. Steve has degrees in mathematics from Caltech and mechanical and aerospace from Princeton. His research combines machine learning with dynamical systems to model and control a wide variety of systems. Many of these are in fluid mechanics, but I've seen applications from Steve in biolocomotion and energy harvesting and even some geological process modeling. So these things have wide applications. He's received the Army and Air Force Young Investigator Program Awards and the Presidential Early Career Award for Scientists and Engineers. Steve's also very well known for his passionate teaching from textbooks to YouTube. So we're really looking forward to both these talks. I think Steve's going to give the first one then, and then we'll switch over to Laura. So please take it away, and thank you very much.
All right, wonderful. I'm assuming everyone can hear me okay?
Yeah, your video's up and we can hear you.
Okay, excellent. Well, thank you for the kind introduction and also for the invitation to be here, and thank you to the organizers. So this is a really exciting forum to discuss kind of this intersection of emerging techniques in machine learning with classical challenging problems in fluid mechanics and climate science. So I'm going to talk about how we can use these machine learning methods specifically for scientific discovery to uncover brand new models, dynamical systems models purely from data that we can then use for our downstream tasks of prediction, estimation, and control. And I want to acknowledge my many excellent co-authors and collaborators on this work. Almost all of the dynamical systems work is done with people on the left, Nathan Kutz, and our excellent postdocs and grad students. And almost all of the fluids work is done with people on the right, especially Jean-Christophe Loiseau from Paris Tech. And so I'm going to jump right in. So fluid mechanics is my passion. It's my applied field of interest. And one of the reasons I love fluids is because it's central to nearly all of our trillion-dollar industries. We literally work and live inside of a fluid, and so do all of our machines. From health to defense to transportation to energy, fluids really is at the heart of many, many of these advanced technologies. And I want to point out that our classic challenges in blue for fluid dynamics are nonlinear, they're high dimensional, they're multi-scale in space and time. And so these tasks in blue, we need to manage the dimensionality. Our simulations often have millions, if not billions of degrees of freedom. And so figuring out some way of reducing that dimensionality and modeling in those reduced coordinates. Where do we put sensors in a very complex flow so that we can estimate and so that we can control that flow? Those have been challenges in fluid dynamics for at least the last 5 decades, but more realistically for the past century. And what I want to point out is that all of those tasks in blue can be seen as hard optimization problems. Again, because the physics is nonlinear, because the physics is multi-scale in space and time, that leads to optimization problems that are very high dimensional, very non-convex. And the takeaway from this slide really is that those optimization problems in pink are the kinds that we're getting very, very good at with machine learning. So if you think about training a deep neural network, that's an extremely high dimensional non-convex optimization problem, but we're getting very good at having these algorithms converge to very accurate models and solutions. And so I kind of see this world of machine learning, if I want to oversimplify a bit, it's just building models from data using either optimization or regression techniques. And those models can be used to solve these problems, these canonical challenges in blue that we have in engineering and scientific systems. And the reason we believe it's possible to solve these tasks in blue, and the reason we believe that it's possible to solve these optimization tasks in pink, is because fundamentally, patterns exist in our data. And so even in very, very complex, high-dimensional, nonlinear problems like climate and atmospheric dynamics, oftentimes we see the emergence of dominant coherent structures or patterns in the data. And those patterns give us some hope of tractable optimization algorithms and tractable estimation and tractable control algorithms. We might be able to model this system, even though it's beyond our ability to simulate at full fidelity, even on supercomputers. And so that's what I'm going to talk about today, is how we build these models. And in particular, I'm going to take just a couple of minutes to give you my philosophy on the kinds of models we want. So we're going to use machine learning to build models of these fluid systems. And I don't just want opaque black box neural network models where you can't see under the hood of what's actually happening. I want machine learning models that are interpretable and generalizable. And instead of defining these quantities, I'll give you my favorite example, which is Newton's second law, F equals ma. This is the quintessential interpretable generalizable model. So clearly it's interpretable because there are 3 terms in the equation: force, mass, and acceleration. And they have units. We can write these down for a problem of interest like a pendulum or a spring on a mass on a spring. We can analyze them, we can solve them, we can discuss them and communicate as humans what these mean. They're highly interpretable equations. And they're generalizable in the sense that you can learn F equals ma from an apple falling on Earth. At least that's how the story goes. And this law is still true when we land humans on the moon. This is the ultimate generalizable model. It still astounds me how much this model generalizes, even though it was learned from simple ballistics on planet Earth. And so these are the kind of models that we want. Surely I could build a deep neural network and train it on videos of apples falling. Maybe I would need 1,000 videos of 1,000 apples falling. But I could train a deep neural network to make new videos of new apples falling, and it would probably fool all of us in the audience. But that model is not going to be useful when we decide to land humans on Mars. So that's what I am hoping that we start bridging in the current decade and in the next decade, is building these models that have this built-in generalizability and interpretability. And this is not just Isaac Newton. This has been the principle of parsimony, the gold standard in physics from Aristotle to Einstein for the last 2 millennia. This has been how we have assessed if something is physical. In fact, a working definition of physical are the bits of the model that generalize well to unseen data. And the way that we have assessed if a model is kind of physical or parsimonious is based on this principle of simplicity. We want the model that is as simple as possible, but no simpler. Again, that's Occam's razor, that's the Pareto 80-20 rule, that's the principle of parsimony, and that is how we have defined what is physical for 2,000 years. And so in the mathematical era, we have tools at our disposal to promote models that have this fundamental parsimony that will hopefully give us interpretable, generalizable models. One of these tools is low dimensionality. So if I have a very high dimensional complex system, can I find the few patterns that matter and only model how they evolve in time? And sparsity. Once I find those patterns and I'm trying to build a differential equation that describes their coevolution, can I do that with as few terms in the equation as possible? The sparsest, simplest model possible, but no simpler. And so that's what I'm going to tell you now is how we are automating this procedure of building low dimensional sparse models that have this intrinsic generalizable and interpretable nature. And so if we fast forward from Isaac Newton to now to the computational era, where we're looking at these problems in fluid dynamics and in climate dynamics, this starts to look a lot like the 1963 Lorentz model for chaotic thermal convection in the atmosphere. So this simple differential equation on the right is designed to model the chaotic behavior in this Rayleigh-Benard convection problem, this very complicated fluid phenomenon that's observed in the Earth's atmosphere. And you'll notice that this model on the right has the two hallmark features we're looking for. It's low dimensional. This model is only written in terms of three variables, x, y, and z, which are the amplitudes of three spatial modes proposed by Saltzman the year earlier. So it's low dimensional. And it's sparse. Out of all of the possible dynamical systems on the right-hand side that you could write down to model this phenomena, this one is quite simple. There are only 7 terms in this model, and 5 of them are linear. It's about the simplest model you could possibly write down to get this chaotic dynamics, and no simpler. So it has those two hallmark features of low dimensionality and sparsity. And what we're going to do is automate the discovery of models of this form, of this Lorentz 1963 form. So I'm going to tell you about how we do this using our sparse identification of nonlinear dynamics, or SINDY algorithm. We wrote this down about 7 years ago, and I'm going to actually illustrate it on that Lorentz 1963 data. So we're going to pretend that we have measurements of the 3 coordinates, x, y, and z, and we can compute their derivatives, but we don't know the equations. So by far the simplest model you could write down would be a linear model, a little 3x3 A matrix that fits the derivatives to the state data, x, y, and z. This is what dynamic mode decomposition does. But we know that a 3x3 linear model with a single fixed point at the origin is not going to be rich enough to capture these full chaotic nonlinear dynamics. So Lorentz has multiple fixed points, unstable periodic orbits, and a chaotic strange attractor. This A matrix has a single fixed point at the origin. It's not complicated enough, so it's too simple. And so what we do in SINDY is instead we augment the right-hand side, the possible terms that could be in our differential equation, to include more candidate nonlinearities that could possibly describe our dynamics. Here I've written polynomials up to 5th order, but you can do anything you like. You can put in Bessel's functions, Airy's functions, trigonometric functions. There's no limit to kind of how creative you can be in building this library of data. Here, and actually for a lot of fluids problems, it turns out that polynomials work really well because Galerkin projection onto an orthogonal basis gives you polynomial dynamics. And so here we're doing polynomials. And so now the key to get simple models, the simplest model possible, but no simpler, is to find the sparsest combinations of columns of theta that add up to equal x dot, that add up to equal y dot, and that add up to equal z dot. 20 years ago, this would have been a brute force combinatorial search. Now there are dozens of commodity sparse regression algorithms that will solve this problem with high probability. And you'll notice that the terms that are highlighted in blue, in red, and in green are exactly the terms in the original equations of motion that generated the data. The unknown equations that we used to generate the data are now being discovered as the sparsest model that describes the data, but no sparser. And so this is true nonlinear system identification, where you learn the structure of the model, and you can do things like prediction and estimation and control using this proxy surrogate model. I'll point out, if you're interested in trying this yourself, we have this software package PySindy. You can try this out on any data set you have, any time series data, and try to build these nonlinear models. Now, you can also start using this to discover partial differential equations. So this is the PhD work of Sam Rudy when he was working with Nathan Kutz and myself, where he generalized the Cindy algorithm. Now, instead of building ordinary differential equations, he's going to build partial differential equations. So given spatial temporal data like this flow past a cylinder, we now build our library to include partial derivatives and nonlinear products of partial derivatives. And so in this case, we're trying to find the time derivative of the vorticity field equals a sparse combination of these nonlinear terms on the right. And when you apply this, this kind of relaxed sparse regression algorithm, you'll find in panel D that the identified dynamics, the dynamics we learn, are actually the Navier-Stokes equations in coordinate form in 2D, with the Reynolds number term accurate to within 1 percentage point. So this is really nice. You can discover partial differential equations from your data now. And I'll point out, because spatial temporal data is so vast, we have so much of it, you can also get away with dramatically downsampling in space and time. As long as you can compute those derivatives, you can still apply this algorithm and learn dynamics. So I'll point out at this point, both of the last two examples I've shown you have been for what we call scientific rediscovery. We knew the answer to the problem, and we used that problem as a benchmark or a test problem to see if our algorithm works. That's how we always start with these methods. But in the subsequent years, our group and our collaborators across the world have been using these methods to discover truly new physics, new models of phenomena that have never been written down before. So for example, the magnetohydrodynamics for plasma physics are an approximation, and it's an imperfect approximation. And researchers are using this method to find new identified dynamics that have additional mechanisms to describe those plasma interactions. Similarly, in the next talk, I believe you'll hear Laura talk about how you can use this in climate problems to get turbulence closures and things like that. So both in incompressible fluids and in climate problems, you can use these to find closure models for turbulent systems. You can use this to model active matter and even neuroscience systems. If you have brain waves or retinal waves, you can find partial differential equations underlying those dynamics. Good. So quick recap. The goal of this approach is to learn dynamics from data, and we want them to be interpretable and generalizable. So that means sparse. So we want either ordinary differential equations or partial differential equations. If I have something like the data from the Lorentz system, I want a 3x3 sparse system of ODEs. If I have data from flow past a cylinder, I want something like the Navier-Stokes equations. That's the sparsest PDE that describes the data. And I'll point out that there's a third option. This is actually much more like what Lorentz did back in 1963, was he took a spatial temporal problem, he decomposed it into 3 orthogonal modes, and then he modeled the amplitudes of those modes as an ordinary differential equation. So that's kind of the third option, to coarse grain a PDE and get this ODE reduced order model out. And we've been doing that in fluids and controls for the last 5 decades. And now you can do that with the Cindy approach. So I'll show you briefly how you do that. So on these two canonical flows of the cylinder flow and cavity flow, what I'm showing on the right, this A delta parameter is basically, it's the magnitude of the shift mode. And you can think of it as a proxy for the drag coefficient on these objects. It's basically a quantity I care about as an engineer that I want to estimate accurately. The white curve is the output of a direct numerical simulation, a high fidelity computation as it evolves in time. And the blue and yellow curves are the previous industry standard models where you take and Galerkin project the Navier-Stokes equations onto either 3 or 7 orthogonal POD modes. And you'll notice that these models are qualitatively okay, but they're quantitatively pretty inaccurate. So this is work by Jean-Christophe Loiseau, I'll point out, in an earlier collaboration of ours where we were extending Cindy to include physical symmetries and physical constraints. So these models on the right are kind of our baseline benchmark comparisons, the industry standard best comparisons. And again, they're quantitatively not accurate enough for our purposes. You'll see that they overshoot. They have the wrong rise time, they rise at the wrong point in time, and they have steady state error at kind of time infinity. So they miss all 3 of these quantitative metrics. But if you look on the right, these Cindy models, and so these are the Cindy models developed by Jean-Christophe Loiseau, these Cindy models almost perfectly agree quantitatively as well as qualitatively. And so they have the right rise time, very little overshoot, and almost no steady state error on the limit cycle. And the way that JC achieves this kind of superior performance is through two mechanisms. So you'll see that there are two curves here. One of them includes constraints. We know something about the physics of the Navier-Stokes equations, namely that energy is preserved through a skew symmetry in the quadratic terms. And so you can actually bake that into these SIMD regressions. So by construction, every model has that symmetry and has that energy preservation. So that's the yellow curve. And the blue curve, what JC realized is that even if you don't constrain those dynamics, you can add higher order polynomials, third order, fifth order, seventh order, ninth order, cubic, quintic, septic, nonic terms. And you can capture the effect of truncated energy from the smaller modes that you're not using and get much more stable, much more accurate modes. Now, what I love about these models is not how accurate they are. Accuracy is great, but they're interpretable, they're sparse. And so you can write them down on a napkin and take them to a Parisian cafe, and you can find this form of the model. This is the actual model of the flow past a cylinder that gives that perfect quantitative agreement. And you'll see that it's very simple. It is a spring mass damper with a nonlinear damping term. It's a van der Pol oscillator. This is, to date, the simplest and the most accurate model written down for this flow past a cylinder. And we get that by adding in this kind of physical knowledge and using machine learning regression. Okay, last slide before I give you my summary and hand off. You can use this for much more complex flows. Those were our simple benchmark flows. We've applied this to more turbulent wake flows like this fluidic pinball. What I like about this example is that we have pretended that we don't have access to the wake measurements. We pretend that we only have access to limited measurements on the 3-cylinder surfaces, just lift and drag, that's all we can measure. And it turns out that you can build these SIMD models directly in those intrinsic lift and drag coordinates, literally DDT of the lift coefficient and the drag coefficient on those 3 cylinders equals some nonlinear function of those 6 coordinates. And in the lower plots, you see that we get almost picture perfect agreement between our low order SIMD model and our high fidelity DNS, which is pretty impressive. So like you can do this with actual measurements you have of your system. You don't need the full flow fields. Okay, I'll point out that we have applied this. I've only shown you 2 examples, maybe 3 examples. We've applied this to a whole host of other systems in the lower left, magnetohydrodynamics fusion reactors. Lower middle, we've applied this to turbulence experiments, full-blown turbulence experiments with our collaborators at Imperial and TU Braunschweig. We've applied this to electroconvection in the upper right. And this is just a selection of a few of the examples from our group in fluids. Really, this is taking off, and researchers across the globe are using this to find new, sparse, interpretable differential equations models for very, very complex fluid flows. Okay, I think with that, I should probably stop talking, and I'm going to hand it over to Laura. Thank you all for listening.
Thank you, Steve. Excellent. So while Laura's getting ready, I will remind everybody that they can find a link in the chat to Slido where they can ask questions for Steve and Laura. Otherwise, I have to ask all the questions, and while I have plenty, it would be great to get some feedback from people in the audience. So that talk was on the small scale, and now we're going to get much, much bigger. Up to ocean scales. So whenever you're ready, Laura, please take it away.
I'm ready. Thank you very much for the invitation. And yeah, thank you also for the introduction. And wonderful to go just after Steve on a beautiful introduction on how to use machine learning in a way that help us capture new physics, being able to understand it, and really trying to push scientific discovery in a way we were not able to do before. So here we're really gonna, basically take a step back in a sense and looking at much, much larger scale, kind of focusing especially on the ocean. I'm a physical oceanographer by training, and really the majority of my work is trying to understand how the ocean works and what is its role in climate. And here I'm going to show a little bit of some work at the core of how can we use machine learning or interpretable machine learning to make advances in understanding the ocean and representing it in simulations. So as always, it comes with contribution from many, many people, especially students and postdocs, both at Oxford and NYU, and many external collaborators as well. So let's look a little bit at a simulation. I think there is nothing better to illustrate the problem at hand. So we're looking at a high resolution ocean simulation on a grid that is 1/48th of a degree resolution. So quite high resolution. And what you can see here is a lot of scales. So you can see here basically a very strong current detaching from Japan. So basically it will actually extend over thousands of kilometers, giving you a large scale circulation. Smaller mesoscale eddies that are about 100 kilometers or so, and then waves that have even smaller scale. So we really have a wide range of scale across the ocean that are all interacting with one another. And all those scales, all that spectrum of scale, will really set how the ocean works and how it interacts with the rest of the climate system. So just to give you a little bit of that spectrum of multi-scale again in pictures, so the majority of the forcing in the ocean is actually really happening at large scale. So you force at the surface with radiation, wind, and you actually generate relatively large scale currents, again, on thousands of kilometers. Now, a lot of those phenomenon, a lot of those large scale currents become unstable, right? So we have really a complex nonlinear dynamical system, as nicely introduced by Steve, and it's the same in the ocean. The slight twist in the ocean is we have rotation, right? So we're on a rotating planet, and the rotation actually of the planet has a very large influence on how those currents, those large-scale currents, can become unstable and actually give rise to some of those vortices here that are balanced or that actually are dominated to first order by the effect of rotation. Now, some of those instabilities can also break up. And here you have basically an example of some of what we call sub-mesoscale on scale of 1 to a 10 kilometer roughly, that are basically predominant in the ocean as well. And of course, you can go on that spectrum to smaller and smaller scale, where you have basically internal gravity waves and dissipation and so on and so forth. So we really are going all across the spectrum with a wide range of scale, all interacting with one another, not necessarily just the large scale breaking up into instability in smaller scales, but also a lot of energy and a lot of momentum that is actually being carried up upscale, right? So some of those small scale instabilities can actually energize the large scale flow and are pretty big and can be a pretty big contribution to the climate system. Now, this whole range of scale is actually determined by our governing equations, and they're the same equations. Complex nonlinear PDEs. So here we have basically the equation for momentum on a rotating planet, right? So here is the effect of the Coriolis force, pressure gradient, gravity. So we heard about F equal ma, right? So this is our F equal ma for fluid on a rotating planet. We're going to have conservations, right? So conservations of mass over here. The ocean is actually, has a density that depends on temperature, salt, and pressure. So that will be our equation of state. And of course, we have thermodynamics equation, right? So we're going to have temperature and salt evolving according to the thermodynamics law. So really a very complex, nonlinear set of PDE that actually determine this entire range of scales that we have here. So this really equations apply to each, parcel of water, also parcel of air, except that the thermodynamics equation and the equation of state will be a little bit different, obviously. Now, if you assume that you take 1 meter cube of seawater, right, and you actually, discretize those equations, you assume you resolve them on the grid box, then you will end up with 10 to the 28 equations just to solve for the ocean. So you can see the range of resolution that you would need, or computing power, to just even solve the ocean dynamic is pretty much out of range for us. So what we do is, of course, we're going to simulate those equations, but we're going to be pretty limited in the resolution that we have if we want to actually resolve it over the entire globe, right? So here are 3 typical, simulations, so to speak. So we're going to take the equation I showed you before, we breaking them down, onto a grid, and we solve them numerically. Here are 3 different horizontal resolution. We're looking at surface temperature. So this is a simulation of surface temperature in a full-blown climate model, run at a resolution of 10 by 10 kilometer. So that's an horizontal resolution, by the way. So 10 by 10 kilometer resolution. In the middle, 40 kilometer. And on the left, 100 kilometer. So those 2 resolution over here, 140 kilometers, are the typical resolution of climate models these days. So you can see that compared to this 10 kilometer resolution over here, that resolve, or at least partly resolve, some of those instabilities that depend on the rotation of the planet. Well, They are a lot more viscous, right? The pictures are more blurry, if you want. It's a little bit, sluggish compared to the very turbulent flow that we should have at that resolution at 10 kilometers. Now, of course, it's not just that the picture is not as pretty when you run at coarser resolution, is we are missing a large chunk of the physics. So we're missing some of those instabilities that are actually critical in steering, mixing in the ocean, but also helping us actually take up heat and carbon and regulating the way the climate system works. And so that not having those scale is actually a pretty big hindrance on the ability of simulating climate, and of course, in terms of climate projections. So what do we do? Well, we don't have enough computing power to actually make those grid box size smaller and smaller and run climate simulation for hundreds of years and have hundreds of them. So what we do is we try to represent all the processes that are not resolved on the grid of a climate model, say clouds, radiation in the atmosphere, or turbulent exchanges, or in the ocean, those kind of turbulent eddies that I showed you before, kind of that detach from large-scale jets. We're trying to represent all those scales that are not resolved by the climate model as a simple, idealized mathematical representation of their effect on the large-scale flow. Meaning, if I take my equation, all right, so in a kind of a simplified fashion, so my partial differential equation, and all I'm going to do, if I only resolve on the coarse resolution grid with the bar over here, I'm going to need to add a force. I'm basically going to need to add an acceleration on the right-hand side that will mimic the effect of the scale that had not resolved on the large-scale flow. Okay, and so you can think about mixing, for example, right, not being present in those climate simulations. So the way we're going to think about it is trying to represent it with a simple mathematical operator that only depends on the quantities that I can resolve on the grid box that I have. So that's really the essence of the closure or the parameterization problem, capturing the effect of the scales that are not represented by the climate simulation that we have because we're limited by resolution, and finding the force that I should put on the right-hand side of my equation to actually mimic their effect on the large-scale flow. And so that's been done for decades. There is nothing new about this, right? So trying to represent those small-scale processes, but the traditional closure based on those kind of idealized mathematical representation have struggled to improve climate models. So they definitely helped us quite a bit. We couldn't do anything without them, but there are still some uncertainties that we can't get rid of. And so the question is, of course, is now we have a sway of data, right? We have new algorithms. So is it possible to actually develop new closures? So trying to capture those representation directly from data rather than in an ad hoc or semi-empirical one. And so really that's an approach that's been taken in the last few years and really kind of exploded, I would say in the last 5 or 6 years, where the idea is to try to take data either from numerical simulation or observation. So right now, numerical simulation for fluids are a lot easier to handle compared to the amount of observation that we would need. Use some machine learning algorithm to try to learn new physics for those closure problems. Lots of examples down here for the atmosphere and for the ocean as well. And as I mentioned earlier, I'm an oceanographer, so I'm going to focus mostly on the ocean. So the philosophy, right, that Steve has already introduced is very much the same philosophy that we've been carrying forward. And so, if we have this kind of very simple paradox of, error versus complexity in the machine learning models that you have, you need to decide a little bit, what kind of model you want to derive. And there is an ocean of possibilities, right? So we can start with something that is physics-based. So you're going to have one parameter and, and a simple mathematical operator associated with it. But the likelihood is that the error in representing the scale interaction is probably going to be large. And that's really what we see in general. Or you can go to something that is extremely complex, like a neural network, where you're going to have tons of parameters. And so you can capture more complex part of the dynamics, but of course, it's deeper, it's harder to interpret. And so for us, the question, really the essence is, if I have a coarse resolution simulation, so, those kind of 2 images over here, what kind of physics or what kind of, closure do I need to put on the right-hand side of that simulator so it will have the same physics as a high resolution run? And then you can see, right, so basically we really are trying to capture relatively important interaction at scales that are larger than the grid box size that we want. So that's what we're going after. So let me show you one example of how can one use deep learning, right? So we still want to capture a model that is relatively complex, but still understanding that there are some errors associated with that model. So let's say we take data from a numerical simulator, and we try to learn disclosure. So we're trying to learn a representation of that missing forcing that comes from those turbulent scales. And so the way we do it is we take, basically an input from the surface velocity of a climate model, and we actually use a neural network to try to learn this missing forcing that we can diagnose directly from a high resolution simulation. So you can see the true forcing is actually quite granular. It's very complex. So you can expect that the neural network will actually do a pretty good job at capturing this kind of rather complex pattern. And it does, right? So in this case, what we've done is we trained a neural network to learn this mapping, right? So given a velocity, what will be the missing turbulent forcing that I need to put on the right-hand side of a coarse resolution model. Now, one twist that we added to it is any mapping that we learn remain uncertain, right? So what we tried to learn was a probability. So rather than learn the full forcing, we learn the forcing plus some kind of, distribution associated with it. So that's one way to try to capture, the uncertainty associated with trying to map a highly nonlinear, function in a simpler form, even though there are thousands of parameters. So that's one way for us to, despite having a model that is deep in terms of the number of parameters that we have, still capturing the amount of uncertainty in that mapping. You can bring in some physics as well, right? So here we're not, we're not using any conservation. The neural network does not know anything about conservation, but it's something that you can build within a neural network, right? So you can actually, modify your architecture. So as mentioned, you can take care of uncertainty, but you can also bake in some conservation properties. So there are ways to approach this kind of, physics-based idea within neural networks, or at least within deep model. But we still can't interpret it. So baking in physics quite often does not mean that the models will be easy to interpret. Now we can try to also capture different parts of, of the problem by looking at latent variables. So Steve mentioned, finding new coordinate system. And so this is work by Sarah Shermack and Pierre Gentine at Columbia. So it's not about the oceans, it's about precipitation. And they do a little bit of the same game that I showed you before. They're going to take high resolution data, they're going to, coarse grain it, and they're going to try to learn basically the amount of precipitation in data that comes from a model. And so their prediction is the orange curve over here. The blue one is the truth. Now you can see it's a little off, right? A little bit off. And so the question is it possible to enhance those predictions by actually focusing on the variables that are the most important rather than throwing everything into the network? And so what they've done is something quite clever, which is trying to actually embed the learning of an autoencoder to really try to capture some of the latent variables that are at the base or at the core of the physical interaction that they're trying to capture. And so they're enhancing their neural network with this kind of idea of finding kind of the best latent variable, if you want, that will represent or capture the physics associated with the precipitation. And now you can see the prediction is so much better. So there is a path, right, with neural network, for example, to capture the right physics that we're missing, the right scale interaction across many dimensions, but they're not sparse. So they're still very difficult to interpret, very different to figure out if they're doing the right thing for the right reason. And so here I'm going to show some examples, following on this philosophy that Steve already introduced is really at the core of the physics or at core of most physics problem. Can we capture models that are sparse, that are easy to interpret, that contain only a few parameters, that will describe the scale interaction that we're trying to capture, and of course, that will improve coarse resolution simulation without or with very little computational expense. So here's one example, very similar to Cindy that Steve introduced, but a bit different. It's based on relevance vector machines. So here the idea is we're still taking spatial and temporal data. So we are diagnosing from a high resolution simulation this missing turbulent forcing that a coarse resolution model should have. We're building a library of functions. So as Steve mentioned, one can be as creative as possible. Now, of course, we're going to be limited, right, with the amount of memory we want to use. And of course, how creative one wants to be might depend as well on what can you simulate numerically as well, right? So there's a little bit of a trade-off there. And what the algorithm is going to do is prune through that library of function iteratively to build an equation for this missing turbulent forcing that we're looking for. So it's really going to be the sum of weights multiplied by some of the basis function that we fed through the algorithm. And so at the end of the day, we of course gonna decide, right, when to cut, how many terms to keep, how interpretable that expression is. But nonetheless, what we're able to extract are weights that multiply some of the basis function that try to mimic, or at least try to capture, the essence of the turbulent fluids on the large scale. Now, because it's a relevance vector machine, it's a Bayesian regression, so there is a bit of uncertainty associated with each one of the weights. So here's an example of an equation discovered with this algorithm that will actually try to capture the effect of those eddies merging and interacting with one another, but only as a function of the coarse resolution. So we took the data, fed it through the algorithm. We cut after a few terms, right, where we felt that the threshold of knowledge, so to speak, was met, where the algorithm could capture the majority of the physics diagnosed from those simulations. And so here what we end up with is a nice symmetric stress tensor that actually captured the vorticity, so basically the curl of the velocity and the stretching and shearing of the fluid element, which is exactly what the turbulence is actually doing in the fluid and how it impacts the large scale flow. So in this case, it's very exciting. We end up with an expression where some of the terms were actually proposed in other papers, but we have some additional terms that teach us something about how the energy actually interacts as a function of scale. So that's pretty exciting, and we're very happy about this. But I would say maybe the downside of it is we still need to preload a library of function. So there are pros and cons about it, right? It's physics, so of course we have some knowledge about what we think the function should be. But here's an example where we don't preload the library of functions. So genetic programming will basically learn a symbolic expression for it. And one way to go about it is to basically, evolve an initial expression that will mimic natural selection. And we're going to go down the tree and we can add and multiply and so on and so forth. And so we can find very deep expression without feeding a library of function. So we actually build upon, GP-learn, which is a technique from genetic programming that is well known, but of course it usually does not deal with physics data. So we introduce spatial derivative, and we actually baked in as well an iterative sparse regression based on residual to try to actually make the algorithm behave a little bit, according to physics, meaning you can't add two expressions that don't have the same units, right? So kind of trying to think about what's possible. And here's one of the expressions we discovered, again, with that algorithm. Some of the ingredients of the one that came out with the relevance vector machine are identical, but we have a few terms that are higher orders. Just a couple of examples. So now in my few minutes left, what I'm going to do is I'm going to show you the performance of each one of those new closures, right? So one that is based on neural network, which has some physics in it, and one that is just a hybrid symbolic expression, right? So basically a learned equation, and I'm going to compare to a physics-based one. So this is a high-resolution simulation. This is the low-resolution simulation, and now all those three are low-resolution simulation in which we are implementing our new closure. So basically, all three of them do well. So this is a physics-based one. This is the neural nets, and this is the hybrid symbolic. So if we look at the amount of energy as a function of scale, actually the CNN performs the best, probably because it's deeper and it captures more of this, the essence of the turbulence in those simulations. And all of them were trained on this kind of configuration where the turbulence is mostly isotropic. Now, if you recall, the set of PDEs that we have should work across the entire ocean, where sometimes we have jets and sometimes it's more turbulence. So what happened if we take the closures that we learned, or the ones that are physics-based, and put them in a configuration that is a bit different, where there are more jets, it's less isotropic. So we want to make this coarse resolution model behave as the high resolution. So here we are. So the physics-based one does very little, right? So it's not going to improve upon the error. The neural network sadly deteriorate the simulation even worse. It tries to make itself more isotropic. And it's not surprising because it's so deep that it learned too many structures that will not generalize well. While the hybrid symbolic that has much fewer parameters and might not look as promising, yet can generalize very, very well. And so we go back to this idea that actually capturing just a few sparse, term, even though might not give you the best R-square, so to speak, when you actually train your model, will be something that probably capture the essence of the physics that can be more generalizable. So there is a zoo of data that one can take, a zoo of algorithm, right? Many outputs, that are possible, many tests that one can look at, and we've done many of them, and I won't go through all of them, from idealized to very complicated. But as I close, I really want to mention a couple of things to try to go back to some of the essence of it, right? So I am a big believer that machine learning and data science have the potential to accelerate scientific discovery, and this was introduced by Steve early on, right? Here I focus very much on the scale interaction, which can span really from meters all the way to thousands of kilometers, and and a way for us to actually improve the representation of many of those scales that are not captured in climate models. And so we have a project that actually look at different parts of the physics in the ocean, atmosphere, and sea ice, to try to get to the essence of what's missing and how can machine learning help us on it. But then I want to close with a couple of comments or questions, so to speak, right? Is when should we blend physics and machine learning, and of course how, right? So first thing is, which outstanding questions in physics can ML tackle, right? If we want to make improvement or discover new physics, we need to know what the problem is. And of course, keep in mind those gold principles that also Steve introduced earlier on: sparsity, low dimensionality. All of this will help with interpretability, generalizability, and so on and so forth, which are really at the core of physics and physics understanding. And so I'm really looking forward to discussions, and thank you again.
Great, thank you very much. So we've now got a 20-minute window for everybody can do their emoji clapping. We've gotten very used to it. We got a 20-minute window for questions. Again, you can go on Slido. While we wait for those to build up a little bit, I thought I would start a question to Laura. I thought it was really interesting to see you talk about uncertainty in these models, because I think that's a big deal and part of the problem, as Steve said, with just getting videos of apples drawing. Like, how confident am I in that video, especially as you showed at the very end, when you switch it to a new case that it hasn't necessarily seen before. And as far as climate stuff goes, we're about to walk into a world of uncertainty. Do I need to evacuate from a hurricane is something that a lot of people have just been worrying about last week. So I wondered if you could talk a little bit about how uncertainty is handled in these models and what's the challenges in that.
Yeah, thank you. It's a very good question, and really definitely one of the essence, right, of making a prediction. Certainty does not exist, right? Especially when you have a highly nonlinear system. All you can hope for is having a probability distribution that you can capture. So in the example that I showed, we made some strong assumptions, right, about the type of probabilities that we were expecting. We made an assumption that, the conditional probability was a Gaussian one. And then we were able to learn point-wise the uncertainty of that, missing forcing. There are many other approaches to do it. Generative models are one way to actually build, some stochasticity in the model, for example, or kind of a way to actually capture many of those images or those videos as uncertainty. And, there are many others right out there. I do believe, we always say that any prediction, uncertainty quantification is at the core of any prediction. And I think there's something we should surely think about quite a bit, especially when we learn in mapping that are highly nonlinear.
Okay, that's great. Thank you very much. Again, really great talks from both of you. I think I'll switch over to the Quora, and Steve's had a longer run for people to write questions. So if you have a question for Laura, please do put it in. So on Quora, the top question for you, Steve, is the issues of, I guess now measurement uncertainty is the question. So if you're dealing with data, how do these models handle measurement uncertainty, not a pristine CFD simulation or something, but something kind of messy and noisy?
Yeah, that's a fantastic question. Usually our data is quite noisy and quite limited. And that's actually one of the, I didn't really mention this, but that's one of the major reasons to use these kind of more classical, simpler kind of sparse regression type machine learning algorithms over something like a big deep neural network where, okay, I'm going to answer two questions. So let's just talk about the quality of data. So there's the fidelity of the data, and then there's also the volume and kind of diversity of the data. And so for deep learning, you really do need this large diversity, large data sets to get good models. And a lot of these sparse regression techniques, because you're fitting so many fewer parameters, you can get away with much smaller data sets, many less examples, and less diversity in the data. For data quality and uncertainty in your data, 7 years ago when we wrote the first Cindy paper, it worked on moderate noise. You have to compute these derivatives, dx dt. And so if you have noisy data, that can be a pretty big problem. We could handle something like 30% noise just using kind of clever numerical differentiation. But since then, researchers, some from my group, some from across the world, have introduced two huge innovations that have allowed us to work with very, very noisy data where the signal to noise is tiny, essentially. So one of these is writing down the Cindy problem in a weak formulation for the PDE. You basically integrate over random control volumes, which averages out a ton of that uncertainty and noise. And the other innovation is ensembling and kind of these random ensemble bootstrapping techniques, which allows you to handle both significant amounts of data and very, very small data sets. So, 5 years ago, I would have been more pessimistic, but in the last couple of years, there have been some pretty major advances to make this work on noisy data.
Great. So that makes sense. The idea that since you're kind of looking for sparse things that are persistent, averaging through the data isn't such a drawback. You can get rid of some of that stuff. That's great. A follow-up question for Steve is, are there any models that Cindy breaks down for, things that it isn't able to do yet, the kind of future challenges?
Tons. I mean, there's more problems it doesn't work than it does, of course. There's no silver bullet problem or a method out there. And if anyone tells you there is, they're trying to sell you something. So I'll just give a couple of examples of things we're working on right now that are super challenging. We can handle systems with partial measurements, like Laura pointed out. You can kind of discover these coordinates and discover latent variables. But sometimes it's harder than others. Like if you're measuring a quantum optics system and you only have the intensity but not the phase, that's very, very hard to back out. Like phase recovery that's again a decades-old challenge that we also struggle with, phase recovery. We're trying to build PDE models for the brain and for retinal waves and kind of neuroscience data, my wife and I, and our collaborators. And in those systems, there's two huge challenges. You get non-local interactions. So Cindy, the simple formulation I showed you involves local PDE dynamics. So non-local is much harder. And also you're dealing with tissue where the parameters are changing in space and maybe in time. That's also super hard. Maybe they have the same PDE, but the coefficient of diffusion and dispersion is different here than here. We don't know how to handle that yet. We have ideas, but those are super challenging.
Great, thank you very much. So a question for Laura, again from Cora. So these machine learning parameterizations, are these already in use in climate models? So have people picked these up? And if not, what do you think are the main barriers for their adoption?
That's a great question. And if I can actually share a slide because I didn't put it. So they are actually being tested as we speak.
You're so well prepared.
There you go. So yeah, so really as we speak. So this is work by Cheng Zhang at Princeton and Pavel Perez-Hogan at NYU. And so right now, of course, they're tested in idealized setting because really our goal right now is actually to test mostly where they break, how computationally expensive they are and what the problems are. So we test them in those very idealized setup where you have basically a square domain, you blow wind at the surface of the ocean, you create a lot of turbulence, and then this is a high resolution run where you have a jet separating. This is the coarse resolution run where sadly there is almost no jet and it's very weak. And those are two parameterization. This is the one that I introduced with a deep neural network and the probabilistic one that already kind of basically really correct for a lot of the coarse resolution run. And this is the equation discovered one that also improve upon the models. So the pros and cons, because I was asked why not. So right now, the deep networks are actually quite expensive. And so they actually slow down the model a fair bit. So we're actually working on ways to make the model cheaper. And that means you reduce the depth of the network, but we also have some issues with boundaries that we haven't dealt with. The equation discover one has some instabilities issues, so numerical instabilities Well, that one we actually fixed, and it's pretty cheap because it's just an equation. So I think, I think they are being tested. I think, it's a long road because, people have been working on parameterization for decades. So of course, we're not expecting, overnight to be able to put them in operational models, but we are definitely testing it. And this code is from the GFDL ocean model, which is used as part of two global climate models used for projections. So we definitely are moving up and actually making global runs right now as well with those. So it's exciting times.
Sorry, classic muting of myself. That's great. Thank you very much. There's one more question for you that popped up just now. So it was dealing with the kind of, I'm going to interpret this as a multi-physics question. So what about kind of how do these sort of models deal with things like ice sheets interacting with the ocean? And I'm sure there's other kind of interactions that are involved in these sort of things too. So how does machine learning potentially help with any of that kind of thing?
Wonderful question. One of my favorite topic as well, really. Yeah, I mean, we have interaction of many parts of fluids, right? So I mentioned the ocean. We work a lot on the interaction between the ocean and atmosphere. And actually, one of the closure that we tried to learn showed that it did very, very poorly near the ice because we were missing some of the key interaction. So really actually retraining the models where you have this kind of true, multi-physics interaction is actually critical because the physics is different. And so this is actually something we're working on. And if you only train in ocean only pieces of the problem, then you are missing the interaction with the ice. And so we saw that actually popping up in those global simulations where, as soon as the ice show up, that's a problem. And I see the second part of the question is projection distortion. Yes, with deep network is a disaster if you use just CNN as is. And there are other methods. So we've been using graph neural network to help with the distortion because you don't need to have basically a fixed distances. But that's also why I really do enjoy the more sparse models because you actually kind of write up your expression with the discretization that you want, so to speak. So it's still discretized, but in a way that you can control in the mapping. So two approaches, both require work, to be clear. Nothing is simple.
Okay, that's great. Maybe I could ask a follow-up to one of those. So you mentioned kind of speed of these. So was that the kind of convolutional neural network was the slower model? Because as you just said, if you have the really sparse model, then isn't that probably not adding too much cost to your work?
Yeah, that's a great question. So the sparse model add almost nothing. And I should mention something up top, which is probably, if there are a lot of computer scientists in the room, they will probably laugh. All climate models are written in Fortran. All operational climate models are written in Fortran. So actually the computational cost quite often is actually this connection between your Fortran code going to the inference step of the CNN and bringing it back. And so your deeper your network, the longer the inference step will be, and then the connection will, between the Fortran and the Python might take longer. So the deeper your network, the longer the inference step will be. But of course, the sparse models are beautiful because, well, I discretize them exactly the same way I discretize any piece of my equation, right? So that's very cheap.
Yeah, I had exactly the same trouble with a previous student who was trying to get Python to talk to Fortran code and trying to use sockets and all kinds of stuff. So yeah, definitely the kind of mundane side gets in the way sometimes. Cool. So maybe one more question for Steve. I see there's a question on what happens when the kind of reduced system that you're trying to build, the lookup table doesn't have the base equation that you need. So if you're kind of missing, or if you're maybe using the wrong family of equations, I guess.
Yeah, good question. This happens. This definitely happens. This happens more often than we would like, where your dynamics are not, a sparse combination of your library. And there's a number of things you can do. Usually building the library is guided by some prior knowledge of the physics that you're looking at. So when I'm looking at fluids problems, I tend to use polynomial libraries because, again, Galerkin projection gives me polynomial dynamics. When I'm dealing with, quantum optics systems, I have terms like U mod U squared and U mod U, cubed and things like that. If I'm dealing with metabolic networks and chemical kinetics, I use rational terms in the dynamics. So we tailor the library to the broad class of physics that we're working with. But even then, still that doesn't work lots of times. And so often you have to couple the dynamical systems discovery with a coordinate discovery. This is something that Laura talked about, is that you can't just learn the dynamics in some any old coordinate system. You often have to kind of rotate or warp this coordinate system, the actual XYZ variables, so that library looks right for those dynamics. And there's actually some really foundational dynamical systems that backs this idea up, this idea of normal form theory, that most super hairy nonlinear systems are a couple of simple coordinate transformations away from actually a sparse polynomial model. And so there is some hope of doing that. That adds a lot of complexity to the optimization. It makes it a much stiffer, harder optimization in my experience, but that is a path forward potentially.
Okay, so I mean, that's interesting for two reasons. I guess that's another way that you can encode physics then, right? Because by knowing that I'm looking in this kind of space of physical things, I will hand it a library which is relevant to that space and not something kind of random or generic. So that's another opportunity to add physics. So that's great, cool. Well, I think we're toward the end. Let's see if there's any more low-hanging questions that have been upvoted. I guess maybe that's a good space to finish. So I will stop there and say thank you very much again to our speakers. I've really enjoyed both talks, learned a lot about climate models that I didn't know before, especially. And I would remind everyone again that it would be great if you thought about kind of going to the next talk as well. Next week, there's one on high energy physics. And look for this video again. It'll be put up on YouTube.